My name is Alex. I work in Vistaprint. Hopefully, you will enjoy today's presentation, but there is a couple scenarios. You can enjoy presentation, you can enjoy pizza, which will about to come, or you can enjoy both. Hopefully, you will enjoy both. Thanks for Vistaprint for organizing this event. And let's start. So today's I'm going to talk about the microservices and on AWS specifically, and some of the challenges you may face during your development. Sorry for that. Okay, sorry. The focus went for the background application. So I'm working with microservices for about 4 years. And this is logo of my team. I hope you like it. So today I'm going to, I actually hate it. Today I'm going to talk about some of the experience I went through, about examples from AWS, because I work mainly with AWS. So some of the examples will be abstract, some would be AWS specific, but I don't think they are limited to the AWS only. So you may find the same examples in in other cloud providers. I have limited experience with other cloud providers, so I can't know for sure, but I'm pretty sure you can. Also, by all means, I don't want to discourage anyone by this topic and listing all the challenges from microservices architecture. This is definitely something which everybody practices nowadays, and everybody strives to do it well. I'm also going to present my opinion, my experience, and the architecture and examples might not be like 100% pure. So if you fight for purity, I definitely don't insist on purity of those examples. So thank you for coming today. And what is microservice? If you Google it, you will find a lot of descriptions and definitions of the microservice. I understand it as a reusable piece of software which reflects a bounded context and structure of the organization. There is multiple ways how to define this bounded context, and there is multiple tools which are described. They are going to be a part of this presentation. So I assume you practice that. You can do that on your own to define these boundaries of the microservice. So a part of this definition, how we normally see, basically what we imagine when somebody says microservice. I imagine this list of principles. First is autonomy. Basically, when you have a microservice, you're supposed to change it and deploy independently without affecting any other microservice in the system, which gives you this autonomy. And microservice cohesive. There is a lot of similar words like high cohesion, dedicated to do one thing well, but basically what it means, it means that your microservice collects somehow similar functionality, and there is one reason to go and change this functionality. If it is true, then perhaps your microservice is high cohesive. Microservice define as a contract which everybody else should obey if they want to communicate with microservice. And microservice normally scalable and resilient, which means that it accommodates all the incoming load and scales horizontally. And in case of downstream system failure, you have a default scenario or a failover mechanism to prevent the cascading failures in your system. Also, when somebody says microservice, I instantly imagine sort of a automation process. I didn't want to put CI/CD there because a lot of people have a strict definition of CI/CD, so sort of automation process which may fully or partially cover CI/CD pipeline to deploy and deliver your code. How we end up with microservices architecture? Well, did anyone have an experience with monolith, actually? Did you like it? So that's probably a short answer for this. So the microservices went through the emerging era of service-oriented architecture. I actually skipped this era because I finished university when the microservices started to practice, and this may or may not be a luck, because actually you experience a lot, you get a lot through your experience. So that might be better to try, or that I would have this experience. But basically, over the years of avoiding monolith application and defining this service sort of schema for your system, people went to the microservices, they started to do it, they understood how it may look like, what are the rules of the microservice architecture, and those basically characteristics somehow reflect those experience of the industry over the decade, I believe already. So some of the challenges one may face when he develops a microservice. Did anyone happen to have experience with AWS here? Okay, so quite some people actually. So the AWS operational challenges is the first one which we go through, which is sort of trivial, and you normally address them with capabilities of either cloud provider or already existing solutions. And this might address, so this basically consists of the challenges like provisioning your infrastructure, defining it, scale it, or define the scaling rules, load balance the traffic, and so on. Architectural challenges, which are more kind of cloud provider agnostic and language agnostic. This is more of a trade-off normally, and basically the majority of the things you decide in your microservice architecture could be a trade-off. There is nothing good or bad about it, you just need to be aware. So the reason I'm going to raise it basically probably to increase the awareness about them. And that might be something like synchronous or asynchronous communication, how to choose basically. When you define a new microservice, how you're going to decide which type of communication you're going to use. This also includes consistency problems in your system when you develop a microservice, and discovery. And distributed systems, which are often referred as fallacies of distributed computing systems, which we will go through in about a minute. So first of all, infrastructure. I put just a couple examples of infrastructure. So there is a huge variety of what infrastructure you can use for your microservice. In my example on the left, we have a ECS with EC2 instances. So basically you provision EC2 instances which are elastic cloud computing from AWS. This is sort of VM. Proprietary to AWS, and you provision these resources to run your Docker tasks on top of them. This is quite conservative infrastructure in terms of that AWS provides nowadays a Fargate, which is serverless approach. So you only handle your Docker tasks instead of resources. But this is more complex, that's why I use this example. But still, there is a lot of services that run on the pure EC2 instances, and you need to scale and spread them across the availability zones. Availability zones is a level of isolation in AWS. So you choose the region you want to run your application, and there is a several availability zone, depends on their hardware. It might be, well, it used to be 2. in the past. Now it's up to 4 or maybe 5 in some of the regions. So if you use your EC2 instances, pure one, you want to spread them across. Also, there is a EKS option for running your Docker containers. Again, in the past, there was EC2 instances, and I think now you can use Fargate the same way as ECS. So the difference between EKS and ECS is mostly that ECS is AWS specific, and whereas Kubernetes is cloud provider agnostic, and it's additional level of abstraction. And a serverless approach, which is Lambda. There is also, so there is a trend towards the serverless approach, and the Lambda was there quite some time already. I'm not advocating for any of these approaches. It depends on the use case you have, but you just need to know about such an options. AWS provides you a way to define your, so once you decided what you want to use, let's say you want to use Lambda because it's serverless, or you want to use ECS because you don't plan to go out of the AWS anytime soon, and you're okay with their Docker containerizing service. So once you decided that, you want to define this infrastructure, and AWS provides you a CloudFormation service where you can set up your infrastructure, spin up it, and tear down. I find it's sort of complex to read. It's a huge nested JSON. So instead of this, for example, in our team, we use Terraform. I love this tool. It's easy. You can split it on different modules and files. And I think it doesn't use this service. It uses an underlying low-level API of AWS, which a lot of things use, including the AWS itself and their SDK. And once you decided how you want to use your microservice, the next step probably to think about what you're going to use with it. This is a list of quite notable and frequently appearing options in the architecture. Basically, the SNS is a simple notification service from AWS. It's a serves pops up architecture, and you normally want to use it when you want to parallelize computing, or you want to fork a sequence of messages. SQS, Simple Queue Service. This is, again, how the name stands. It's a simple service. It's not a message broker. So you normally use it for sequential asynchronous processing inside of your microservice ecosystem. And S3, Simple Storage Service from AWS. This is a key object storage. Both three are highly available and very scalable, and they have a deep integration. So you basically can loop them together. You can send notification from S3, let's say, to SNS and fork it to several SQS, and then read these messages and so on. So the deep integration of the AWS services is quite nice. A part of this, you maybe need to use a database, and DynamoDB is an AWS NoSQL database, or cache, and AWS provides Elastic Cache, which comes with Memcache or Redis. You need to decide in the configuration. So the next part comes is when you decided what you want to use and how to want to operate, you need to define a set of permissions. AWS have their role model where you define the role, you define the service which can assume it, its service retrieves the temporary credentials, and they advise you to use this role model. And when you specify this role, you basically can include a specific permissions of low-level API, and you can limit it to the principal or the specific resource. The next thing is scalability. When your microservice needs to scale, And while the horizontal scaling is not that trivial, the vertical is not that trivial, the horizontal one is opposite, quite trivial, and everybody use it. And you can use AWS auto-scaling service to set up basically your scaling of your microservice. If it's EC2, it's going to be one scaling, EC2 basically scaling group. If it's ECS, it's going to be two. One would be an application scaling, which going to scale your application and spread it on the resources you provide. And the first one going to allocate the resources. They're going to be totally independent, so you need to sync it or think about the metrics you use for both on your own. If you use Fargate, you need to just think about the application scaling, and that's it. Load balancer. So when you define how you want to scale, you probably want to spread the traffic towards the resources you have. Auto-scaling going to register all the new spinned up instances on its own to your load balancer, and you need to define the load balancer. AWS currently provide a new generation of two load balancer, the network load balancer, which basically routes the traffic, and the application load balancer, which is more smarter. If you need more smart way of routing your traffic, you can use it, and one of the features you can use let's say path analysis, or you can check the headers of the HTTPS request. On top of that, the load balancer have a not really friendly DNS name, which is automatically assigned if it's internet facing. So you want to assign something more user friendly, you can do that with route 53 and CNAME. So far simple, right? Looks like it is. So where we were talking about basically only operational things around your microservice. And where the complexity comes, it's what I described is basically a manual of AWS. Everybody can read, understand. It just takes some learning curve, but that's it. When the complexity comes, the complexity actually comes when you have multiple microservices. While I didn't enjoy working with Monolith, to be honest, it was quite easy to debug and navigate through the code stack. You don't have this luxury when you use a microservices architecture. So when I first started with microservices architecture 4 years ago, I actually was drawing a map of all the interactions of 20 microservices to kind of memorize if something happens where I need to trace this, this distributed transaction or even the request kind of routing. Let's take a look on small example of microservices. We have only two, so I can't imagine the smaller than that. One of the things is I'm putting just a thing there saying microservice, but it could represent any kind of infrastructure, and I assume there is load balancer if it needs to be, there is scaling already set up, so we don't basically touch this topic anymore, and we try to think what other challenges we can see here. So first of all, which comes to my mind is we have two microservices A and B, and they communicate with each other. So microservice A needs to be aware of microservice B. So there is supposed to be a discovery mechanism which would explain service A actually where to direct its call. And there is several approaches here. AWS released their whitelist, which I came across about 1 year ago. It covers the complex discovery mechanism you can build on top of AWS. But generally, what you want to do is, if you have a very simple case like this, probably the hard coding, the DNS is okay for you. If it emerges or you have a dynamic way of introducing a new microservice, you need to sort of mechanism to register it and serve it to everybody who is interested in this, which may be, for example, a key value storage, which is updated constantly, or it could be a microservice dedicated for that, actually. So in my previous experience, we had a whole dedicated microservice for that. And on the startup, each microservice resolves its dependencies, and it kind of verifies that they're still actual. Also, if you take down, with this kind of system, if you take down your microservice, you need to assume that there might be still propagated old DNS. Another thing is microservices is effectively a distributed computing system. It means that it's subject of all the problems distributed computing system can introduce you, and this very often referred as fallacies of distributed computing systems. And we are not going to cover all of them, but the main is the first four, basically. The network is not reliable, so when you communicate over the network, you need to have a mechanism to address a network failure. And the simple one could be a retry. There is one more, which is quite often referred as a circuit breaker. Another one is latency. So if you have two microservices, A and B, and let's say microservice B is a customer microservice or order microservice, and for some reason microservice A needs to get a batch of the customers or orders, it's probably a bad idea to get them one by one. Since the latency is not zero, it will take some substantial time. So you want to account for that, and if there is such a requirement to prepare a batch endpoint to ship all the information or use pagination, which you define with your team. Bandwidth is infinite. So I don't know if anyone saw a problem with the bandwidth on the production microservices. Okay, I see a couple hands. So this is quite rare to come across because normally the network allows you to almost infinite, but I also experienced that and it was completely not evident. So for some reason, microservice gets to really slow into sort of unhealthy state, and it took us some time until we filtered the metrics according to the traffic to see actually that some of the requests are so huge that they almost kill the entire microservice. And the security. Our previous talk was dedicated towards the security solely, so I'm not going to stop on this topic. You can watch it on YouTube in our channel. Basically, you just need to be aware that the network is not secure, and normally it's handled on the organization level, so there is a sort of security your microservice needs to plug in and honor. Another thing to keep in mind is CAP theorem, which stands for consistency, availability, partition tolerance. And basically what it means, if you have a distributed store, you can choose only 2 among 3. And since all the services of AWS strive to be highly available and they are partition tolerant, you basically end up with eventual consistency or inconsistency with your read-write operations. So when you architecture your microservice, you need to think about it and take a look in the consistency model of cloud provider service you're going to use. For example, S3 is a subject for eventual consistency. It has read after write model consistency with the caveats that all the subsequent writes will be, or deletes will be subject to eventual consistency, and if you try to get some key, even the first write is going to be an eventual consistency as well. Actually, if you have any questions, you can stop me throughout the presentation. Do you know what how actually eventual consistency can arise in your system? Did you ever tested it or saw it? Somebody? No? Did anyone want me to write? Okay. So basically, if I'm going to duplicate it a bit. Again, AWS documentation, a part of being confusing in navigation is quite good. So let's say we have write 1. And if we go in, yeah, it's right. If we go into, and this is the timeline, and we go into read it, we're going to receive a consistent data, which means we are going to read our write 1. But if we try to read it here and read it once more, we can get 2 things, null and our consistent object. And it comes similar with a couple writes, let's say. So in this model, we are subject for eventual consistency, and when we are going to read, we're going to end up with any of those and the null. So any of this is a possibility for our service. Normally, this doesn't happen, but you need to remember if your microservice very close to the underlying service, and it's subject to eventual consistency, and you have extremely high response, the changes might not propagate. So if there is an almost no latency between write and read, you may find yourself in this situation. So I guess we went through the eventual consistency. To be honest, before the presentation, I tested it. So what I did, I wrote a very simple web API, and this web API sequentially writes and reads several times. It took me about 15 minutes of running load test, to be honest, but it was very light load test, and one of the threads basically read inconsistent object. I was comparing the hash. This is also a nice feature. You basically can either specify a hash, and S3 will verify that this hash is propagated, or when you write, they give you a hash, which doesn't have to be MD5, but they state it's MD5. So you can compare this. When you write, you receive it as a response, and when you read, you also see a hash. So you can kind of compare it. S3. No. As far as I know, it does not. Sorry? Yes, if you're not read before. If you read this key, you listed the keys. Yes, and I'm saying it is until you try to read it before you wrote it. So if you try to read it and then first time wrote it, it's still going to be an eventual consistency. For S3, yes, even for the first write. It's somehow bonded to their internal implementation, which they obviously doesn't want to expose. There is like some speculation and theories, but there is no official documentation like why this happens this way. So one of, sorry, is there another question? No. So one of the also frequent things to use in your microservices is caching mechanism, because you would like to improve your throughput or performance, and there is also a standard way and a lot of patterns which covers that, how to cache it. But essentially, if you need a cache, you normally will come to Elastic Cache Service. And you just need to think in advance if your data is okay to be stale. If it's not, maybe you need to have so-called a write-through approach where instead of having dependency only from one microservice, microservice A, you would have to bring dependency of Elastic Cache to the microservice B. And once the microservice B receives a new data update, it's going to push it through to the Elastic Cache. There is also TTL, which you can put on top of Elastic Cache, and you can definitely use all of them at once, or one of the patterns. And one of another things which I wanted to mention is central logging and monitoring. Did anyone try to run a microservices architecture without centralized logging and monitoring ever? No? Well, I had this experience, to be honest. And when something happens, it could take like millisecond to an issue will arise, and you'll spend up to 3 days collecting the logs, concatenating them, joining them. So it's quite horrible. So if I would know this 4 years ago, I would probably enforce the centralized logging and monitoring straight away, at least logging. The monitoring is nice, but it's kind of work, non-work state of your system. So when you want to see if it works or non-works, you go to the sort of dashboard or anything else that combines and pulls metrics. And this allows you to instantly see if everything okay or not. But when you need kind of a story of what happened, and in distributed systems, you really need it from time to time, then you need a centralized logging. And when you use it, there is also a good practice, which kind of enforced good practice, to use a transaction ID or correlation ID. Otherwise, it's very easy to lose the track of the logs, unless you have a very smart centralized logging system with, let's say, event sourcing. This is actually the test of eventual consistency I did before the presentation. Again, 15 minutes. And so I used the same object per thread. It means that I was not accessing it concurrently. But if you access object concurrently, it's like on 10 requests with 2-factor concurrency, pretty much 30% will give you inconsistent data. Okay, so I will try to now share the example of real system. But one may be surprised how a developer could be bad with a PowerPoint. So I have pictures of AWS with arrows, but I don't have a picture of real system. So I would try to explain you a context of the system before coming into it. So let's imagine we have a website for advertisements like selling a house or selling a flat, sort of things. And our website want to basically retrieve the data from the user, which he posts, and have an advertisement bounded context to verify, enhance it, structure, and have a proper way of doing this, and most likely with API exposed for that. But additionally, a part of this website, you may have another website, and you may have partners or clients from the agencies. When you want to sell your apartment really fast, you go into multiple channels, and these multiple channels can come to the same point of data. And so there might be also a third party or in-house as well tools connecting and also specifying this data. And basically, if I would think about it straight away, it's like, okay, we have a defined context. Someone did it for us, or we did it as a team. So the simple way would be to kind of came up with monolithic API to do this functionality and maybe split it later on once we understand how it works. Maybe after a couple months or 1 year, depends on how it goes. And it could look like something like this picture. This is a real thing you need to do with advertisement, but it's not a real architecture. I'm using this just to kind of show how it may look like if we need a simple synchronous services to address this. So we have basically our gateway to this domain, which is a REST API for advertisements. We have a quality service which checks the quality of the data. We have a taxonomy service to kind of structure, tag, and do other taxonomy things with our data. And let's say we have also a geo service to kind of append a geo information to our advertisement, because this is a very frequent element or parameter in the search. So when you search, you want to search it at least in the same city. You don't want to search in different country. And GeoService has also its own dependency on GeoIndex, which is propagated and used for that kind of purpose. So, and once we did all of this, we went through this circle, we persist the information, and our advertisement is done, and we give a synchronous response. So, what is the problem with this architecture? What is the main obvious, at least, problems with this architecture? Sorry? Where exactly the bottleneck? You mean on the left, right? But what if we scale it to accommodate our demand? Yes, definitely, but we can scale horizontally. We need 20 instances. We threw it away because this is a demand. We have to accommodate it. And maybe analyze and learn through the experience what to do with this information. Anything? No? That's one of the things. So we come again to the fallacies of distributed computing. And the first one is network is not reliable. We have a synchronous request-response architecture here. How easy do you think define in all four, and we have only 4 here, microservices, this failover mechanism where we either retry or implement a circuit breaker, what we consider a default response in case of one of the services is down. Can we, for example, skip the quality check if it's down? Probably no. Can we skip a taxonomy? We'll see. So one of the biggest challenges of the synchronous architecture, as I see it, actually this not reliability on the network and embracing the errors. But on the other hand, we have a very simple flow, and we have a synchronous response from our system. So our clients definitely sure that it worked, or it didn't. And let's go a bit towards the real system that was there. So actually, this was thought through, and on top of that, there was another thing. Since we have multiple sources of information, definitely we're not going to have millions of posts from the website, unless it's malicious attack. But from the in-house tools or integrated services, that's definitely a possibility. So our load can change, let's say, from 10 posts per minute or second up to, let's say, several 100,000. So in that way, it's really hard to scale your synchronous application, and even keeping in mind that the provisioning is very good, it's quite fast, there is still going to be a percentage of these requests failing, kind of enforcing your microservice to scale up. And once your microservice scaled up, it's going to drag other dependencies with it. So again, some of the percentage is going to fail until its dependencies is going to scale up. With this architecture, I didn't finish it on purpose. We avoid this by having a a message queues in between, and simple AWS queue was tested for the throughput and performance, and apparently it's close to non-degradation, even with millions of the requests. So now we have this architecture, and first of all, which you can see from here is it's simpler in terms of the communication of the services. Basically, our services doesn't need to know about other services. It knows about the previous queue it subscribed, it knows about the queue it publishes the message, and we have event-driven system effectively from here. So we can basically retry the amount of times we want without being afraid of losing the information. We can sorry, let's probably go to the questions to this from me. So actually, what do you think is the problem of this architecture apart of more complexity, because we introduced more components into that? So a part of the microservices, now we have also the queues. What do you think is a problem here? Latency? You mean the whole process? Yes, I mean, definitely there is a strive towards making it as fast as possible, but on the other hand, we receive a pro. Again, this comes to the use case, but the pro of this would be that we don't lose anything, and we get as many things we can, scale as we need, especially if we have couple services dependent on scaling of each other. And the SLA also is problem with the synchronous. I mean, if you start to increase load, your services start to give slower and slower performance. So yes, but I think it's an equal concern for two of them.
You need to know your consumers.
Sorry?
You need to know your consumers.
What?
If you want to notify anyone about your event in this architecture,
Yep. Yeah, well, definitely there is a way to do that. For example, in this case, there was an SNS topic. Yes, which is not described here, but that's, again, this partially intentional. Yes, definitely the systems which are publishing or posting to the API, they need to somehow retrieve the information that everything actually went okay. And they retrieve it either from the normal flow or through the error flow. But let's, again, take a look on this, and we have several steps. Do you think it's a good idea to process the message? So let's put an ID in the message. So we store the state of something that comes before we even start to process it. We put an ID in the message, and we store the partial data after each step to our persistent storage. Do you think it's a good idea? Why? Exactly, but let's say we went through two steps. We went through quality checks. We maybe did some enhancement in taxonomy. We saved it to the persistent storage, and the geo is down. And it's like unrecoverable, and for a long time. And we retry, and we keep retrying. It doesn't help. We reach the threshold of retries, we throw away the message, or we leverage AWS functionality to do so for us, and we discarded it. What we end up in our system now is actually a partial data, an inconsistency, because we went through the half of the steps, and we persisted this information, but we didn't finish it. I see. Okay. 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 So you mean some local storage to store it, but what you're going to do with this? So let's say, okay, all the consequent, or even your service, it saves this state before it starts to work with this, and it constantly fails. What you going to do with this state? In general, in event-driven systems, it is encouraged, but as I aware about the use case of such when you do an event sourcing, so you don't really persist the state after you finish an operation. Okay. Okay. The question was basically you have a persistent storage where you store your advertisement. So is it a good idea with each step kind of finish its operation and store the result in this persistent storage? Let's say the first one stores the advertisement with taxonomy, the second one reads it, stores the advertisement with geolocation, the third one reads it, stores with something else. But in central persistent storage. Not the local one, the central. Yeah. Generally, yes, you don't share the storage, and this is the first bad thing, but it also kind of, I understood your point, but my question was a bit towards this sharing the storage kind of thing. And this is the first thing, and then it's rule of thumb, you don't share the storage. But even if you need to think about the distributed transaction. In our case here, if we fail to process the message in the middle, we kind of threw it away, and we mm-hmm. Either this, or transfer the whole state with a message. So you can put the whole state in your message, and it means that all the flow going to take it from the message, not from any storage. And if everything goes okay, in the end, we drop it in our persistent storage, and we have two states only, either nothing or all the steps were okay. So this is kind of a natural distributed transaction out of the box with putting your state in the message. So basically, that's what I was trying to convey. And one of the things which I saw in this system is, for some reason, sometimes there were a portion of the messages that you can't process. So you retry, it allocates the resources of your microservice, it occupies it, but it doesn't do anything because it's destined to fail to process this message. So when there is such thing arrives, there is either again a retry mechanism threshold or out-of-the-box functionality from AWS, which is dead letter queue. So now you don't need to retry on the messages. You can specify the letter queue, and after several attempts, it's going to go away. One of the also aspects of such a system, duplication. So SQS naturally can provide you a duplicate data depending on how you're pulling, but even if you use a long pulling, there is a chance that some node going to go down during your polling request time, and once it's come up, it doesn't know about you taking this message out, so your duplication can naturally arrive in your system. And what is the best thing to deal with duplication? Yes, that's true. This is a, well, yes. What is, exactly, what is the trade-off? Do you know about the trade-off of this queue? Throughput. Throughput. Yep. Well, exactly once delivery is a big luxury in distributed systems, and there is definitely trade-offs which comes with them. With this queue, it's basically it is content deduplication if you don't change the content. So you can specify this feature and it's going to automatically deduplicate the content. It's true. But if you change, let's say, a timestamp on one of the steps, it would not be able to deduplicate it because the content is changed. But what is the kind of common practice to do that? I already touched it with the change in the content. What is opposite will be is idempotent operations. So you just, if you can, make sure that with any number of the same messages is going to lead you to the same result. In that sense, you don't really care the duplicates which can arrive with your bug or with AWS at least once delivery in their queues, because you always consistent in your results. So you're going to process the same message a couple of times, you're going to override the data, but it's going to be the same. So your consumers of this data wouldn't know that there was a duplicate in the system. Distributed transaction, how do you think, so now we were talking about the single message that was thrown to our system. What if our supplier or third party gives us a file, not the single advertisement, but a file with the rows, and we would like to have a transaction on top of that? Well, you yes. You need to design something on top of that. So in our case, there was basically a separate transaction generation which was attached to each single entity in the file. But what if the half of the file was successfully processed and there is a transaction success per half of the advertisement, but half of the file failed and were discarded? Yes, or yeah, yes. But what do you think you can do with that? Because, well, business people is definitely not happy that half of the jobs failed and they want you to, you have the file, you are not going to manually split it. Well, you definitely can, but it will take some time. Yes, this could be part of the requirement. In our case, there was a kind of redo, undo mechanism, which takes basically everything according to this specific transaction. And since we don't want to end up with half of the file, so we will undo it, which means we will go into route all the advertisements with a delete mark in front of it. They're going to be persisted as deleted, and then we're going to process the file again. This was the thing, and to be honest, it was working quite well. The overall, I had a very pleasant experience with this system, to be honest, and this architecture, a part of complexity and centralized login, as I already mentioned. Until there was a new requirement, which basically broke this nice ecosystem of idempotent pipeline with natural distributed transaction and everything. Let's say we have a couple people or a person and the company, somehow third party, give you the same advertisement. And what if multiple companies do that? So you want to have a business deduplication, figuring out that this is actually the same information. You don't want to flood your search with the same advertisement. You want to give to the user only the one that's relevant and hide everything that duplicates it. Also, there might be multiple rules in place for payments. For some you pay more, for some you pay less. So there is a business enforcement in that. And that pretty much broke this logic, to be honest, because now when you transfer the state, together with this state, you also specify a different entities, which might be in any stage of the pipeline or the persistent storage. Do you understand the problem? Yeah, I will try to go through the problem again. So let's use our example. So we have two advertisements. It's the same, but two different users or a service account and the user post them. So if we don't have any duplication, we sequentially process them. The first example, we sequentially process them without anything, thinking it's two different things. With the second, they can come together or close to real time together. Again, we process them. And this basically goes through all the list without deduplication. But if we deduplicate, the rules were actually quite complex because there are multiple scenarios how to do that. And I will try to do my best to explain you, but apparently it's not that easy. So let's say we process the same advertisement in the pipeline. None of them persisted. You need to understand that somewhere in this pipeline already the duplicate. And you need to somehow decide which one is going to win. And by the end of the operation, only one of them should be active and one should be non-active. And this is complex scenario because you didn't persisted one. When you persisted one, you can always ask, okay, let's create some sort of microservice which gives us this similarity property of multiple entities. So you ask with one of the entity, it gives you the list of persisted ones, and you can decide. But when you process and in parallel, this is really hard to do that. Is it a little bit clear, basically? So what you can't do here, you cannot, in the middle of your pipeline, you cannot start to decide which state is going to be changed, which one is going to win, which one is going to be active. Because if you do that, you break this nice distributed transaction. And if you have two advertisements and you do that along the way or while they processed, you can end up with both active, both inactive, and you can actually make it worse. Before you implemented some kind of rules in the middle, all of them would be live. It's maybe annoying for some of the users, but there won't be any information loss. But right now, we actually made it worse because it could be any of the combination of active, non-active multiplied on amount of duplicate jobs. And we did our best to do a idempotent operation. So one of the things were to, again, make a idempotent operation, so it doesn't matter how many times we process it, we end up with the same winner. So that's this way we can kind of avoid inconsistency which we bring to the system. But what was completely ruining this idea is deleting. Because again, there is no order of deleting the advertisement. So you delete one in one thread, you delete another in another thread. So one thread thinks the winner actually the non-deleted one, and another thread you have another non-deleted job. So it was completely ruining the thing. So what was the solution? Or it might not be even a solution, but what we investigated again, through the multiple mentionings in the universe of microservices, is when you have an inconsistency in your system, you can try to do an event sourcing. It means that you don't really change the state of an object, you build a log of the changes, and then something comes, grabs this log, and decide what actually the state should be. This way you avoid these constant changes, and actually it was also bringing the problems because the notifications for the consumers were coming with different information. It could be like both at the same time. This advertisement was deleted or non-deleted. So we try to build an event sourcing mechanism on top of that. And the best part of event sourcing mechanism, you don't have to have it everywhere. That's actually not advised to have it everywhere unless you're absolutely sure you want to design your system with event sourcing. So instead, we took this scope and said, okay, we are not going to do anything. We're just going to make a decision. We're going to throw an event, and something is going to slice this log for the similar advertisement and decide. And while it's slicing and deciding, nobody's able to append to this log. So there was two things to do to allow this kind of thing, is event sourcing and distribution locking. And basically the event sourcing, what I've read, doesn't really imply you don't need to store a state of an object at all. It's you can store the state and the backlog on top. You can take the backlog and change the state until the new backlog will arrive. And I read about the trading systems which actually take the backlog every day, and they change the state of the system and they do a snapshot. And they store actually a backlog only for 1 day, not for all the time of your system. So a couple words about distributed locking. Basically, this was meant to prevent a concurrent access to the log of events while you're slicing it. And it doesn't really that complex as it sounds. You just need to spin up something where you're going to lock on the property, like on the string. But since we know that the only thing that bounds to advertisements is kind of a similarity property, so you need to lock on this similarity. And you need to, when you normally lock with the distributed locking, you want to prevent, you want to operate in mutually exclusive manner. So it means that only one thing can acquire the lock. And there is actually a multiple implementation already for DynamoDB, for Redis, I'm pretty sure for another cloud providers. But what generally happens is you have two threads or instances which would like to lock, and the lock is acquired only if more than half of the instances of your cache or some nodes you're locking with give you a green light. So if 2 out of 3 your cache nodes is returning you that the lock is acquired, the lock considered to be acquired. And if it's not, you want to fail fast and try again or try on a different one. So basically, what we end up with was this architecture is instead of making any state changes in the middle of the pipeline, it was appending to the Redis if it can acquire the lock, and sending a message. And there was basically two flows. One is the normal one, which just persists the data, and another one which, instead of persisting, slices the log, decides, persist, and release the log. Is there any questions regarding that? Yes. 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 It designed to be fast. There is multiple. We used a Redlock one, so there is a manifest which describes in details all the technicalities of it, but basically it designed to be very fast, because the faster you acquire the log, the less chance that you can run in the situation when multiple instances or thread race for the same log. So it's supposed to be extremely fast. Since there is only some subset of advertisement, not really big one, was suffering from this problem, not really. And that was pretty much all the examples from me. This was the most, let's say, difficult I ever experienced. I'm really glad I worked with this. It gave a lot. For example, introduction of event-driven systems, and basically 3 types of them. Yep. Summary.
You say in your design, you are not saving state of the, let's say, request, whatever, in persistence database. You are storing it in the queues, and at the end you store in the database. Right?
Sorry?
When you receiving the request from the, let's say, REST API, you storing it in the queues, and after every step you process it, you storing it in the persistence
Yes.
database, right?
Yes.
What if, for example, it's failed, but before you charge customers some amount of money, and you don't, after it's in dead letter queue, and like after some time, you will lose this, and you first you charge customers, and how you will handle this situation?
So the charging mechanism, to be honest, I'm not really familiar with charging mechanism, but the idea of charging mechanism was on top of tagging. So it was mostly like per clicks charging, and I don't think users were charged. So it's more like for the companies. So all the clicks were attributed with a token, and according to that, the bill was formed. So if you don't end up with something persisted, it couldn't be clicked, it couldn't be found in the system, it couldn't be clicked, you couldn't be charged for that.
Okay, so you make charging at the end of the process?
The charging was kind of a part of this process.
I haven't seen that you are charging customers, but if it's advertisements, I suppose there is some charging.
There is some charges, definitely, but as I am aware, the majority, like payments, were from the third party or the one who provides directly to the API, because the users, you want them actually to come to you and put a lot of advertisements. That's how your resources are grow. So, but I'm not a selling person, to be honest, so I'm not sure how the motivation was working.
My question is not regarding my question, but actually the automatic charging process. So imagine, for example, let's say I have worked in Telephone area. What we have done was if like customer subscriber send SMS first, we are charging it.
Okay.
We providing the service. I suppose you had similar approach. That's why it was my original question.
Well, you can always just block on the credit card the amount of money, then you can provide the service, and when it is successful, only then you can accept pay.
Yeah, check this one way.
To be honest, I was not working with the transactions, so the summary, I guess we went through most of the bullets here. Is basically favor independent operations where you can in the distributed systems. Try to keep things simple. So, for example, keeping things simple is identifying a small scope where you need to go complex-wise and introduce event sourcing. Don't change other part of the system. Once you receive some technical problem you can't easily address, there's still a lot of solutions you just need to dig. And thank you.
So two things. First one, our next meetup is gonna be on Thursday, May 30th, and it's gonna be about AWS API Gateway. And second one, pizza is about to arrive, so grab some drink on a bar and wait for it for a while. Sorry.
Actually, I didn't ask if anyone have a questions. You can ask. Yeah. Okay, so the question is, did we try a message broker instead of the queue? Personally, I didn't. The team did. And the results was that the message broker degrades over a certain threshold of the messages. So I'm fairly certain the RabbitMQ was tested. So the comparison was it degrades a lot comparing to the AWS queue. Yes. I will per second I can't say, but let's say 5 millions per day, like 2 millions per day, 5 millions per day, but there could be in the short period of time. It doesn't have to be. So I was monitoring it on the daily basis mostly, and for example, I mentioned this undo-redo mechanism. So by some mistake or skipping the filter, you could wrote all the advertisements to the beginning of your pipeline, and it could be like millions. I would love to, if actually you can, actually, if anyone can share some information, like for example, you're not sure in something, or also take into account this is, let's say, at least year late information, and with 1 year, a lot can happen in the industry and services that cloud provider gives you, especially AWS. No, I think nobody can follow all of the features they release. So if you have information or comparison up to date, please share. I will be happy to see it.
Do you have a CI/CD pipeline?
Yes.
What tools do you use for these companies?
So in this project, there was a DevOps team, and there was an in-house tool for that. So what I know is it was the standard blue-green deployment, as far as I can tell, but the details were hidden. So everything was basically happening the same way. The instances were doubled. You test them, and if you see everything okay, you switch them to the new instances. You switch the traffic to the new instances, and if something wrong, you turn it back. Yep.
What's the reason for you to use the
Well, the ECS was in the preview, I believe, at that time. So, and the Kubernetes was not even in preview. So there was just no capability. For the ECS? Okay, I see. I can't find any, actually. I find somewhat a strange of enjoy set up in my EC2 cluster, but if you don't find the same joy, please use the serverless. It actually saves you a lot of the trouble. For example, if we compare it in the lines of Terraform, you will lose 30% of the lines of code to use ECS without EC2. So.
And I think Lambda function is more costly when processing. You're continuously processing the depends on how much you use. But in that case,
It's true, but sometimes you don't know how much you will use. And the funny thing about the AWS billing is it's nearly impossible to calculate your costs before you actually start to use. So sometimes you start to use, you find it expensive, and you try to substitute it with something else. So maybe the cost would be a decision factor, but setup-wise, definitely Fargate have an advantage. Why? You mean, but you cannot run the container on Lambda, at least without hacks. Yes, you can run your direct code. Again, no reason. The architecture for this. Okay, so the architecture for this was during the time when the Lambda .NET Core was just released, and the majority of stuff was in the classic network. Net framework. So the main reason was actually the code base. So you even if you rewrite in microservice, although it's quite easy, it will take some time for the team to basically, you saw the components and the pieces of the system. Yeah, so classic .NET. Okay, thank you very much and enjoy.